Morning, folks.
Good morning, Praveen.
Testing. Okay, looks like we're all set up. Okay, good morning, folks. Sorry, I'm running a couple of minutes behind here. So not much in the way of logistics to talk about this morning. Just one thing on my list, which is homework 5 has been posted. This is one short problem on perturbation theory, just so that you get a chance to practice and apply the things that we're talking about this week and next week. Let me take a moment and share screen. and I will show you what is on homework 5. So here is the assignment. Homework 5 is due next Friday, the 5th, which is also your last day to submit any back homeworks that you would like. Because next Friday at about midnight, I'm going to post all solutions for all homeworks to date so that you have them to study by for the midterm. So here is homework 5, due next Friday, only one problem long. So overall, worth 10 points. The first part is relating to the harmonic oscillator. Given the harmonic oscillator, the regular harmonic oscillator, consider a perturbation which goes like x to the 4th. This is referred to sometimes as the anharmonic oscillator. I ask you to calculate the first order correction to the energy. This looks like a simple formula, but it actually takes a significant amount of algebra to work out. You will work out essentially matrix elements of x to the 4th in terms of creation and annihilation operators. So it's not nearly as much algebra as working through the Runge-Lenz vector on homework number 4, but don't underestimate this. You're going to be doing a lot of commutation of A and A dagger. So once you've solved this and you have the value of the first order perturbation, I'm asking you to assess when perturbation theory is good. Perturbation theory is good as long as the perturbation is small compared to the ground state of the unperturbed Hamiltonian. So if this is the first order correction to the energies, you already know what the 0th order energies are, the regular energies of the harmonic oscillator. Compare those, the ratio of what you have at first order versus what you have at 0th order, and look at that as a function of n. You'll find that at a certain n, the correction becomes bigger than 100%. And at that point, you should definitely not trust perturbation theory anymore. The whole thing is based on the idea of a Taylor series, where the coupling constant in the perturbation is small. So find the value of n beyond which the correction is above 100%, and you should definitely not trust perturbation theory. And then last, just sort of visually, if you sketch a plot of your x squared potential for the harmonic oscillator compared to the x to the 4th potential of the perturbation, it should become clear that sooner or later, the perturbation is going to become larger than the original Hamiltonian was. So I'm just asking you to make that connection between the x dependence of the potential and the n dependence of this ratio and argue why it doesn't matter how small your coupling constant is, sooner or later perturbation theory is going to break down for the anharmonic oscillator. So this is worth 7 points, the majority of it. The second problem, or the second part of it, is even simpler. This is an explicit 2-level system. You have an electron, which is spin 1/2 in a magnetic field. This should look very familiar. You've got a large magnetic field along the z-axis, B0, and a small perturbation along the x-axis. So you're treating the x perturbation as small compared to the z unperturbed Hamiltonian. Calculate the first and second order shifts in the energies. Calculate the first order correction to the wave functions. That's it. Any questions on homework number 5 or other logistical issues that we should discuss? Okay, great. If not, then let's remind ourselves what we talked about on Monday. We started with a discussion of time-independent, non-degenerate perturbation theory, and we derived the most important formulas that you will need to use under pressure at first and second order in perturbation theory. So the idea is you're doing essentially a Taylor series of the exact eigenvalue problem in terms of some small coupling constant, so that your fully nonlinear eigenvalue energies, En, are decomposed as the unperturbed ones plus a correction linear in G plus a correction quadratic in G, and so on. Just a reminder of the notation, the superscript here is not an exponent. This is just an index reflecting what order in perturbation theory you're talking about. And just as a reminder, I am here explicitly writing coupling constants G. Shankar does not write coupling constants G. It doesn't matter. It's just a useful tool to keep track of what order in perturbation theory you're talking about. So last time we derived the first and second order corrections to the energies. The first order correction to the energy is just the expectation value of the perturbation in the unperturbed states. So you have a state n, it gets hit by the perturbation. There's some probability that you stay in the same state n. If you stay in the same state n, that acts like a shift to the energy. At second order in perturbation theory, you have 2 insertions of the interaction. This means that now for the first time at second order, it's possible to start in the state n, jump away to some different state m, and then jump back to the same state you started in n. So you have this transition amplitude squared, reflecting a jump and a jump back. That combination puts you back in the same place that you started, and that effectively diagonal piece contributes as if it were a correction to the energy. So this piece has a double jump in the numerator, and that denominator is an energy denominator. It's the difference between the energy you have in state N0 and the energy that you're borrowing to jump temporarily to state EM. And I'm going to argue that that's related to a time scale, and we'll see how that arises as a time scale today when we talk about the interaction picture. So similarly, you can work out the corrections to the wave functions. The wave functions we only evaluated to first order in perturbation theory. This is all you're really expected to know and reproduce under pressure. You have the 0th order wave function, and the correction to the wave function at first order reflects that jump from the state you start off in, N, to any other state, M being different from N. So you're summing over all states different than the one you started off in. Again, you have a transition amplitude. You have an energy denominator reflecting the lifetime of that quantum fluctuation. One thing that we found was that at first order in perturbation theory, that this perturbed or corrected wave function did not overlap with the one that you started off with. In principle, there could have been some overlap, but it was non-physical. There was no actual subtraction of probability in the original state coming from that first order jump to the next state. Generally, at higher orders, there will be corrections where if you add probability to be in a different state, you have to subtract the missing probability from the original state. But at first order in perturbation theory, that doesn't happen. So after you remove an irrelevant complex phase, which is the only thing that happens to this original state, you can consider the perturbation to be orthogonal to the original one. Okay, any questions on what we discussed last time before we go to the interaction picture? Okay. So last time I tried to set this up before we moved on. We said we would like to consider what is the time evolution of states in perturbation theory. So here we're going to be talking about time dependence, but this is not the same thing as time-dependent perturbation theory. The perturbation that we're talking about here, this H1, is independent of time. And we will be looking at the time evolution produced by that time-independent perturbation. So this is different from time-dependent perturbation theory. Okay, so we know how to write down the time dependence. The time evolution operator is given by the exponential of the Hamiltonian. This comes from solving the full time dependence. Given by the complete Schrodinger equation, I h bar dt psi of t is equal to the total Hamiltonian h naught plus g h1 psi of t. And the solution to this differential equation, because this is time independent, is just given by the exponential. So psi of t is given by e to the minus I over h bar, the complete Hamiltonian h0 plus gh1 t, acting on the original state psi of 0. And this is the full or dressed propagator. Full dressed time evolution operator. And just like I did a moment ago, I will often slip into field theory language and talk about this as if it were a propagator, describing how a particle or how a state created at one initial condition propagates through space and time. This whole idea carries over very cleanly to field theory. Okay, so this is the solution, but this is not very helpful because this exponentiated form contains all orders in G. And so we would like to essentially expand this behavior and solve it order by order in G. That is not very amenable in the normal lab frame, you might call it, because the time evolution is governed by both the non-perturbed Hamiltonian and the correction. So the way that we will approach this is to shift to a time-dependent state, similar to going to a moving frame of reference, that will eliminate the time dependence from H0. And then we'll get just an operator that depends on H1. And then we will be able to expand that order by order in perturbation theory. So this description of the time dependence is known as the Schrödinger picture. That's the one we're usually working in. This is the one where the states are time dependent, and most of the time your operators are not. What we are moving to now, this evolving frame of reference that we're about to write down, is referred to as the interaction picture. So I would describe this as a moving frame of reference that moves with H naught. So the clearest way to see the impact of the perturbation is in a frame of reference where the non-perturbed Hamiltonian is not doing anything. So this exercise algebraically is very similar to the exercise that you guys did in homework number 2 for paramagnetic resonance. We have the full Schrödinger equation given by this thing. So we will define an evolving state, a time-dependent state. All right, the state that I have, psi of t, is given by the time evolution u of t, and I'm going to write u naught of t here. This is the time evolution of the unperturbed Hamiltonian, acting on the interaction picture state, psi I of t. So this time evolution operator we know very well, e to the minus I over h bar, H naught, the unperturbed Hamiltonian times time. And this is my definition of the interaction picture wave function. And so I would compare this to what you did for homework when you wrote state in the lab frame was given by the rotation operator u of minus omega tk, omega naught tk, times psi rotating of t. This was that transformation to a rotating frame. So in the same way, I'm going to take this definition of the time-dependent state and plug it back in to the time-dependent Schrödinger equation. And if we have defined the frame that we want correctly, then when I plug it back in, this will remove the contribution from H naught and give me something simpler. So when I plug this back in, I have IH bar dEt, this time dependence is U naught of t psi I of t equals H naught plus GH1 times, let me write this as U naught of t psi I of t. When I take the derivative, I have to worry about product rule. The time derivative can hit either the interaction picture state or it can hit the time evolution operator itself. So when I take this derivative and I plug in what u of t is, this is, let's see. I have one term where I have IH bar e to the minus I over h bar h naught t, and I differentiate the state. ddt psi I of t. The other term is the one where the ddt hits the exponential itself. That's going to bring down a factor of minus I over h bar, which exactly cancels the IH bar in front. So the second term that I'm going to get is plus h naught e to the minus I over h bar h naught t psi I of t. And this is going to equal h naught plus gh1 e to the minus I over h bar h naught t psi psi I of t. And if we define this correctly, then the h naught contribution should vanish. So does it? I have plus h naught minus I over h bar h naught t. And on the right-hand side, I have plus h naught e to the minus I over h bar h naught t. So this term cancels this one, which is what we intended when we defined this state in the first place. And so what I'm left with is e to the minus I over h bar h naught t I h bar ddt psi interaction picture equals gh1 e to the minus I over h bar h naught t psi interaction picture. And I can solve this equation to write something that looks like the time-dependent Schrodinger equation for the interaction picture. And I get I h bar ddt psi I of t is equal to e to the plus I over h bar h naught t gh1, the perturbation, e to the minus I over h bar h naught t times the state, psi I of t. So this object is the time evolution operator u naught dagger of t. This one is u of t, u naught of t. So the thing that governs time evolution in the interaction picture is this combination u naught dagger of t, gh1, u naught of t, psi I of t. So this looks like this is my transformed Hamiltonian. Just like we said for the transformation of operators, you have u dagger operator u, that is reflecting the transformation of the operator. And since the state is defined with the non-perturbed time evolution operator, that is what transforms the perturbation. So this object acts like the Hamiltonian of the perturbation in this moving frame, in the interaction picture frame. So this is GH1 interaction picture I, which has been transformed, and it is time dependent now. Psi I of t. So this is equivalent to writing down the Schrodinger equation in this moving frame of reference, where we are absorbing the time dependence of the non-perturbed Hamiltonian. And the effect is it rotates or it transforms in a time-dependent way what the perturbation is doing. So physically, you can think of this like you have the harmonic oscillator. You know what the natural states of the harmonic oscillator are. There are states that are oscillating back and forth like sine and cosine. Now imagine you're sitting on that spring in a frame of reference. It's a non-inertial reference frame that's moving back and forth. In that reference frame, the regular harmonic oscillator part is doing absolutely nothing. And if you have now an anharmonic correction to the harmonic oscillator, now in that moving frame of reference, every time you see that spring jiggle, that jiggle is caused by the perturbation itself. So this is a clear way to see what the perturbation is doing. The price you pay is that your frame is time dependent. So the solution to this equation is not just exponential of this Hamiltonian because this is time dependent. Still, it's not much harder to solve, or at least to formally write a solution for it. So I'm going to call this solving the equation, but it's really just transforming a differential equation into an integral equation. So I'm going to take this expression and I'm going to solve it for ddt. So I have ddt psi I, I'm going to suppress the t's from now on, equals, no, maybe let me not suppress it just yet because I'm going to change the dummy index. Psi I of t equals minus I over h bar interaction Hamiltonian h1 I of t. Psi I of t. So this is my equation and I would like to integrate it. The way I'm going to integrate it is first I'm going to replace t with t prime. Just relabel all t's with t primes. And now I'm going to integrate this expression, dt prime, from 0 to t. So when I do that, on the left-hand side, I have a perfect differential that's just evaluated at the endpoints. So this is psi I of t minus psi I of 0 equals, on the right-hand side, I just have some integral. I can't do anything else with it. Minus I over h bar integral dt prime from 0 to t gh interaction of t acting on the state psi I of, these are t primes. So I have integrated the Schrodinger equation, and this looks like I have solved it. I haven't really gained any information about it. I've just transformed the differential expression into an integral expression. So this integral expression is the same as the time-dependent Schrodinger equation written on the right side, or my right side, your left side. But this one is actually much nicer because I can take this expression and solve it recursively. Right, so I have psi I of t on the left. Psi I of t is also here in the integrand. So this is not really a solution. Right, solution on the left gets plugged into the integral on the right. That's bad. This is not a beautiful solution by itself. But if I take this expression, psi of t equals psi of 0 plus an integral. So now inside that integral, this thing is equal to psi I of 0 plus another integral. And that thing is going to have another psi in it. And that thing is equal to psi of 0 plus another integral. So I can construct the solution recursively. Before I do that, I want to draw a picture that goes along with this, because this integral structure is something that is easily understandable. Yes, sir.
I had a question. So, doing that thing and finding the solution as a recursion, it won't give an exact solution to it because we'll still have to terminate it somewhere.
That's correct. So this is an approach that is well suited to perturbation theory, where you have the intention to truncate the series eventually. This is not a good strategy for obtaining the exact solution. But exactly as you say, if G is a small number, then I can justify stopping that recursion relation at finite order. And so that's how we will obtain the perturbative expressions at given order for G. Okay, maybe let me transform back to the Schrodinger picture now. This was what we needed the interaction picture to write down. Now let's go back to the regular Schrodinger picture. So let's transform back. From psi I to psi in the Schrodinger picture. So my definition was psi of t is u naught of t psi I of t. So where I have psi I of t, it's going to be u naught dagger of t, psi of t. This is my inverted transformation. Notice that if t is equal to 0, psi of 0 is the same as psi I of 0. Psi I of 0 equals psi of 0. The two frames of reference coincide at t equals 0 by construction. All right, so if I take this thing, my psi I of t on the left-hand side is u naught of t, psi of t, u naught dagger of t, psi of t. There we go. Equals, this is psi of 0. There is no difference between psi I and psi at t is equal to 0. Minus I over h bar integral dt prime from 0 to t g h1 interaction picture of t. And now I'm going to plug in both of these factors. So this is psi I of t prime. This psi I of t prime is u naught dagger of t prime psi of t prime. That was this transformation here. I also have the transformation of the Hamiltonian. This time-dependent Hamiltonian came from u naught of t prime dagger GH interaction, H1, the perturbation in the Schrodinger picture, u naught of t prime. So this simplifies things, right? So this u dagger u with the same t prime cancels. And I have this factor of u naught dagger of t on the left. I just multiply it through to the right. This gives me that recursive iterative integral equation back in the Schrodinger picture. So my solution is psi of t equals u naught of t psi of 0 minus I over h bar integral dt prime from 0 to t. I have u naught of t, u naught dagger of t prime, gh1 psi of t prime. And last, I can just combine these two time evolution operators, right? This one evolves you forward in time by t. This one evolves you backward in time by t prime. So more specifically, this is e to the minus I over h bar h naught t times e to the plus I over h bar h naught t prime. The only operator in here is h naught. H naught commutes with itself, so I can safely add the exponents together. So this is e to the minus I over h bar h naught t minus t prime, which is just u naught of t minus t prime. So time evolution is additive, the same way that translations are, right? You translate forward in time by t, backward in time by t prime. Overall, you have translated by t minus t prime. Okay. Having made this transformation back, we're done with the interaction picture for now. This is what we needed it to construct. The solution psi of t looks like the first term, the 0th order term in G, u naught of t, psi of 0. This is the term where the time evolution comes entirely from the unperturbed Hamiltonian. This is what you get if you turn off the perturbation. Plus an extra time dependence that comes from the perturbation itself. Minus I over h bar, integral dt prime from 0 to t, time evolution, 2t from t prime, gh1 psi of t. So I can draw a nice picture that helps me understand what this recursion relation is telling me. If I start off with a quantum state psi of 0, and I'm evolving that thing forward in time, and later on I find the state psi of t, how does it evolve from 0 to t in the fully interacting picture? So I'm going to write this as a big thick line here. This represents the full dressed propagator, full dressed time evolution. So this means that the time evolution from the initial state to the final state is given by the complete time evolution operator u of t. No 0 downstairs. And what we've written here is a decomposition that says the full propagation is equal to bare propagation from psi of 0 to psi of t. This one is the propagator in the non-interactive, the unperturbed Hamiltonian. This is u naught of t, the simple one that we know the answer for. Plus, the recursive structure is given by this term. This one looks exactly like, let's see, you start off with some propagation from psi of 0 to psi of t prime. At psi of t prime, something happens. You get hit one time with the perturbation. So right here, you have a vertex, gh1. So whatever's going on, something complicated, this is equal to one interaction with the perturbation, and then after that, free propagation from there to psi of t. So think of this like a diagrammatic representation of this equation. This thick line is the thing I don't know the answer for, but I can construct the thick line out of the thin one that I do know the answer for, plus something involving the thick line again. So diagrammatically, what we're going to do is we're going to construct this solution order by order. And I'm going to write this as bare propagation plus, now if I take to first order in this recursion relation, replace thick line by a thin one. This looks like bare propagation, one interaction, bare propagation. The second order correction is the part where this thick line has a second interaction buried in it somewhere here, plus one interaction, second interaction, all with bare propagation inserted in between, plus dot, dot, dot. So each of these visual elements corresponds to one piece of this equation, unambiguously. This line is U naught of T, something that time evolves you in the non-interacting or bare Hamiltonian. Each of these vertices is exactly one insertion of that perturbed Hamiltonian. And so by building this up, I build a whole series that says I have 0 interactions, 1 interaction, 2 interactions, n interactions. This is a visual representation of perturbation theory. 0th order perturbation theory, 1st order perturbation theory, 2nd order perturbation theory, and so on. Every order in perturbation theory comes along with one extra insertion of the interaction Hamiltonian in this time-ordered way. So the beautiful part about this is that there's a one-to-one correspondence between the mathematical expression and the visual representation in terms of diagrams. This is the basis of Feynman diagram notation. All of this is a little bit overkill for what we're going to actually use it for right now, but this sets up how it will be used in more complicated situations in the future. So next, what I want to do is I want to write the equations corresponding to this picture. I want to write out the first couple of iterations of this. So if I just take psi of t and replace it with psi of 0 plus another integral, then what I get is psi of t is u naught of t psi of 0. The first order piece is minus I over h bar, integral dt prime from 0 to t, time evolution, t minus t prime, one interaction. If I just take this and I replace this with psi 0 of t, psi 0 of t to first order, or to 0th order is just bare time evolution. So this is u naught of t prime, psi of 0. So this line corresponds to this diagram. This says you start off with a state at psi of 0. It evolves forward in time from 0 until time t prime. At time t prime, it gets hit by the perturbation. After time t prime, it continues evolving forward in time until it reaches time t. And any time in between 0 and t is when that insertion could have happened. Yes, sir.
Just to make sure, should that psi of t have a e of t prime?
Oh, thank you. Yes, I keep doing that. This is t prime. This is being integrated. Thank you. So this insertion corresponds to this diagram, plus the second order correction. So we had minus I over h bar, integral from 0 to t, dt prime, 0, t minus t prime, gh1, and now I'm inserting another copy of this integral. This next integral comes with minus I over h bar and a new integration, dt double prime, from 0 to t prime. This one looks like bare time evolution, to T prime from T double prime, a new interaction GH1 times psi of T, right? And that psi of T I'm replacing with U0 of T, psi of 0. So here I'm plugging it in where that time is T double prime. So this is U naught T double prime psi of 0. Plus, technically, if I don't want to truncate the series, I have to keep on going infinitely. But every time I iterate this recursion relation, I get something higher order in G. This is G to the 0. This is G to the first. This is G to the 1, 2 powers. So corrections to this expression are order G cubed and higher. So this is the complete propagator that I will need to get all results at second order in perturbation theory. So let me clean up this second line. This is U naught of T psi of 0 minus I over H bar integral dt prime 0 to T. Bare time evolution from T prime to T. One perturbation, bare time evolution up to T prime psi of 0. Plus, the second order correction has overall minus I over H bar squared. Double integral dt prime, integral dt double prime. T prime goes from 0 to T, T double prime goes from 0 to T prime. These guys are nested. And then overall, that string of propagation that I have is U naught T minus T prime, one interaction, U naught T prime minus T double prime, another interaction, U naught of T double prime. Initial state, psi of 0. And corrections are order G cubed or higher. So that second expression corresponds to this diagram, 1 to 1. I have an initial state psi of 0. I have bare propagation from there to T double prime. At T double prime, it gets hit by one perturbation. From T double prime, after the perturbation, it evolves again from T double prime to T prime. There it gets hit by a second perturbation. And then after that, it evolves freely from T prime to T until it reaches the final state. So these integrals are nested in such a way that it's describing time ordering. This is saying T double prime is the time the first interaction happens. T prime is the time the second interactions. It happens later. And you're integrating over all allowed times from the first one to the second one, and so on. So this is the picture that I wanted to give you about what perturbation theory is. This is the cleanest way that I know of to think about perturbation theory, that you have a state which is sitting along, minding its own business, just propagating according to the free Hamiltonian. And then at first order in perturbation theory, you are dressing this with exactly one insertion of the interaction. Could happen at any time in between, but you only add one. At second order, you are hitting it with two interactions, any time in between, and so on and so forth, to reconstruct the entire perturbation series. And if you had the ability to sum all infinity number of diagrams, all infinity number of terms from this recursion relation, you would reconstruct the complete time evolution, which is the dressed evolution operator given by this thick line. Let me pause here and see if this conceptually makes sense to you. I don't want this to just be an exercise of getting lost in the math. My goal in getting you to this is not for you to be able to reproduce this time evolution under pressure. Like I said, this is one of the most powerful sets of machinery in quantum mechanics, and this is really useful when you talk about calculating high order corrections, third, fourth order perturbation theory, when you need time-dependent perturbation theory, where your H now has time dependence of its own. In that picture, that's not going to change. You're going to have H of T prime sitting in here. Right now, the order of this is dictated by the commutation relations, that you have this operator, that operator. But you can see if this became time-dependent, it's just going to sit right here and have a time dependence in it. Nothing more is going to change. Okay, the next thing that I want to do with this is I want to use this expression, 0 first order, second order, to rederive the formulas that we already constructed last class to show you how they arise from this time-dependent picture. Hopefully this will help add some physical intuition to those formulas. So let's start with the first order recursion. So time evolution at first order in perturbation theory. So I'm going to use u of t is approximately u naught of t minus I over h bar integral dt prime from 0 to t u naught t minus t prime gh1 u naught of t prime. So this is that kernel, this is the thing which multiplies size 0 if I only keep that first line in the perturbation series. Plus order g squared. So let's look at what happens when you act on an eigenstate. So consider n0 u of t n0. So this should have physical interpretation. You start off with state n naught. It evolves with the fully interacting Hamiltonian up to first order. And then I ask, what is the amplitude at some later time t that I find it still sitting around in the same state n0? I'm going to take this expression and I'm going to sandwich it between those eigenstates. So this is equal to n0. This operator is e to the minus I over h bar, h naught t, n0. That's the zeroth order in perturbation theory. Minus I over h bar, integral 0 to t, dt prime. This one is e to the minus I over h bar. Oh, for the states. n0, e to the minus I over h bar, h naught, t minus t prime, gh1 times e to the minus I over h bar, h naught, t prime, n0, plus order g squared. So I've taken this expression for the dressed time evolution operator and I've sandwiched it between eigenstates. For the zeroth order expression, the answer is simple. Because n0 is an eigenstate of h0. So this term is just e to the minus I over h bar, the energy of that state, en0, times the overlap of those states, which is 1. Likewise, I'm going to use the same kind of statement to talk about this Hamiltonian acting on that eigenstate, this Hamiltonian acting on that eigenstate.
Just to make sure both of those are e to the negative I over h bar, right?
That's correct. Yeah, so I've written it as forward time evolution. This is evolution forward in time from 0 to t prime, and then evolution forward in time from t prime to t. Forward time evolution is e to the minus I over h bar.
Okay.
So the first term that I get is e to the minus I over h bar en0t. This is exactly what a stationary state is supposed to do. The probability is constant as a function of time. The state just oscillates with a complex phase. That complex phase comes with e to the minus energy times time. For the second correction, I have minus I over h bar, integral dt prime from 0 to t. This first factor gives me the number e to the minus I over h bar, energy en0 t minus t prime. And the state hops past it because this is an eigenstate. So I end up with n0 gh1. For the ket, again, this is an eigenstate, so the state hops past it and h naught gets replaced by the energy. This is n0 times e to the minus I over h bar, the same energy, En0 t prime, plus order g squared. So all of the quantum states have been pulled past and they're sandwiching the perturbation. These are just numbers. E to the minus I over h bar, En t minus t prime cancels e to the minus I over h bar, En t prime. This one and that get canceled. The remaining factor depends on t, but not t prime. This one can now be pulled outside the integral. Not only that, it's the same one that I had at 0th order. So this is e to the minus I over h bar, En0 times 1 minus I over h bar. This matrix element is also time independent. If h1 depended on time, it would have to stick around inside this integral. But it doesn't because this is time independent perturbation theory. In fact, nothing depends on time anymore. Nothing depends on t prime. I just have integral dt prime from 0 to t plus order g squared. This integral is the simplest one you can have. This is just t. So my expression is e to the minus I over h bar, bare energy, times 1 minus I over h bar, matrix element of the perturbation, times time, plus order g squared. Order g squared, this first term is equivalent to the exponential. So I'm just going to write this as e to the minus I over h bar, n0 gh1 n0t plus order g squared with the same accuracy. These are not operators, these are just numbers. So I can combine the two exponents and I see that this matrix element acts to effectively shift the energy of the state. So my final expression is n0, total time evolution. n0 equals e to the minus I over h bar, bare energy, En0, plus that matrix element of gh1 in the state, plus order g squared. Or maybe put the plus order g squared downstairs. T, plus order g squared. So this is what we mean when we talk about correcting the energy. The probability that you get hit by a car with the perturbation theory, with the perturbation, but still land in the same spot you were standing when you got hit, that correction acts like a correction to the energy. So this is the contribution that comes when you have bare evolution, GH1, and you were in the same state before and the same state afterwards. This correction acts like a shift to the energy. En0 plus N0 GH1 N0. So this is how I think about what the first order correction to the energy means in perturbation theory. You do not have to use this full machinery to derive that. You can just use the expression the simple way we derived it before. But I think the intuition that comes from this is very powerful, and it helps me wrap my head around what perturbation theory is. You can repeat this exercise. If you go back and you keep the second order in perturbation theory, then you get two effects. We don't have time to go through this today, but you get the second iteration of this. You get one term that looks like g squared t squared, which is the second order piece in the Taylor series of this exponential. And you get another term, which comes from the second order in perturbation theory, something that's order g squared and linear in time. And that acts like the second order correction to the energy. So the other thing that I want to do is I want to take this expression and evaluate the same thing, but now sandwich between different states to get the correction to the wave function at first order. Any questions about this? Okay. All right, so the second thing that I wanted to do with this is for a state M, which is different than the state that you started off with. Now I want to take that evolution operator U full of t from some initial state to a different final state. So this is given by m0 e to the minus I over h bar h naught t n0 minus I over h bar integral dt prime from 0 to t matrix element m0 e to the minus I over h bar h naught t minus t prime gh1 times e to the minus I over h bar h naught t prime n0 plus order g squared. What is the first term going to give me? 0. Why?
M and N are different states.
Yes, because M and N are different states. These states are orthogonal to each other. So each of these states is an eigenstate of H0. This just pulls out in front. This is e to the minus I over h bar, let's say En0t, M0, N0, and this guy is equal to 0 because M and N are different. So there is no contribution from the zeroth order in perturbation theory to this transition amplitude. Obviously, by definition, the eigenstates of the bare Hamiltonian are diagonal for the bare Hamiltonian, so it cannot cause transitions among its own eigenstates. Only the perturbation can do that. So when I evaluate the second term, I have minus I over h bar integral dt prime from 0 to t. This first piece, it looks very much like what we did before, but now the energies are different. So it's not going to combine in the same way. I'm going to have e to the minus I over h bar em naught times t minus t prime. And then I have the matrix element m0, gh1, n0. This last piece is going to be e to the minus I over h bar en0 times t prime. Now my t integral is not trivial anymore. Plus order g squared. So let's clean this up. So anything that does not depend on t prime can come outside the integral. This first piece, e to the minus I over h bar emt, that one can come out. This matrix element, by assumption, is time independent. That can come out. The thing that cannot come out is this phase factor that depends on t prime. So what I have is minus I over h bar, the matrix element, n0, gh1, n0. I have the bare time evolution, e to the minus I over h bar, em naught t. The piece that's left inside the integral is integral dt prime from 0 to t. I have e to the minus I en, e to the plus I em. So this is e to the minus I over h bar, en0 minus em0 t prime. When I do this integration, I'm going to get 1 over minus I over h bar, en0 minus em0 times the same exponential e to the minus I over h bar, en0 minus em0 t prime evaluated on the limits from 0 to t. First thing I should worry about is, oh my God, what if the denominator is 0? And then I remind myself the denominator is not 0. Why is the denominator not 0? Because these are different states, and this is non-degenerate perturbation theory. I have guaranteed myself by the assumptions that these are different energies, so this is safe to do. If it was not safe to do, if this energy was 0, I could still do the integral, but I'd get a different answer, right? If this difference were 0, this integral would be 1, and I would just integrate it to get t. In this case, I don't, because they have different energies. So, very conveniently, minus I h bar and minus I h bar cancel each other, and I get something that looks familiar, m naught GH1 N naught divided by an energy denominator, En0 minus En0. And I'm left with some funny combination of time dependence. En0 times time, this exponential in the brackets is minus I over h bar. En0 minus En0 times time minus 1. So this is e to the minus I over h bar, En0 times time minus e to the minus I over h bar, En0 times time. And this is my final answer. Plus order g squared. So the piece that I want to make sure that you understand here is this first factor. You have the transition amplitude and you have the energy denominator. That energy denominator comes from integrating this time evolution. You have two different plane wave states that are oscillating with their own different frequencies given by En and Em. That difference of frequencies means that you have some complicated interfering wave function. And this thing is most closely peaked when, let's see, the amount of time you're integrating over is like 1 over this energy, right? So you have some oscillating function. When this exponent is close to 1, or sorry, when the integrand is close to 1, you get the dominant contribution. So the typical lifetime of this state, where this exponent is not too big and oscillating very quickly, comes from 1 over En minus En. This is my interpretation of this as a lifetime. Now, you have some annoying time dependence left over that I don't have a simple interpretation to give you. Probably if you wanted to derive the exact formula, you would need to take the limit when time goes to infinity to ask about the transition from the infinite past to the infinite future to lie in a given state. That limit is clearly non-trivial for these kind of functions, so I'm not going to touch that right now. But I wanted to point out where this factor comes from. Is this part clear? Okay, we've got about 10 minutes left. I have a couple of examples, simple examples on how to use perturbation theory that I wanted to work through. I think maybe I've got time for the simpler one. Yes, sir.
In the bracket, shouldn't it be En0 minus En0 in the exponents? The other way around? In the final formula that you wrote?
Oh, here. Yes, sorry, excuse me. This is all 5 minus sign. Thank you. That's correct. All right, simple examples. So this one is actually taken directly from the 2017 comprehensive exam. Although, frankly, this is an easy enough problem that I essentially gave it to my undergrads in 395 for linear algebra. Comprehensive exam. So given a bare Hamiltonian, which is diagonal with two different energies, E10, 0, 0, E20, and a perturbation, GH1, which is purely off diagonal, B. With, just for the sake of concreteness, the second eigenvalue is bigger than the first one, and both of them are positive. Also, B is much smaller than any of these other things. E10, E20, smaller than the difference between them. It's small with respect to everything, but it's still positive. So the exercise here is find the first and second order corrections to the energies and find the first order correction to the wave function. This problem is so simple you can solve it exactly. And that's a good testing ground for perturbation theory. Let's start by applying the formulas that we derived last time. The first order shift in the energy, En1, GEN1 is the matrix element between the original states and the perturbation. So to do this, first I need to know what are the eigenstates of the original Hamiltonian. The thing is already diagonal, so the eigenstates are obviously 1, 0, and 0, 1. So my original eigenstates, I'm going to call this 1 to 0th order, is 1, 0. The second state to 0th order is 0, 1. The corresponding eigenvalues, I read it off because they're already diagonal, is E1, 0, and this one is E2, 0. So when I'm talking about this kind of product, I'm literally saying, take that column matrix and sandwich it around this perturbation. So this thing is literally just 1, 0, 0, B, B, 0, 1, 0 for the first state. And for the second state, it is literally 0, 1, 0, B, B, 0, 0, 1. Both of these expressions give me the same answer. Both of them are 0. When you look back at it, that should be obvious. The perturbation is totally off diagonal. If I ask, what is the matrix element in these diagonal states? There is no diagonal part. So it has no first order shift to the energies. The only thing that it does is a second order shift to the energies. My formula for the second order energy shift, En2, which comes with a weight of g squared, is the sum over all states m different from n, m0, gh1, n0 squared over En minus Em0. Thankfully, this sum is not very big. I only have 2 states. So if I'm asking for the shift in energy 1, I can only be talking about the state energy, the state number 2. So GE1 at second order, this summation is just a single term. 2, 0, GH1, 1, 0, squared over E1, 0 minus E2, 0. So this is 1 over this difference. By assumption, E2 is the larger of the eigenvalues. So I'm going to write this as negative 1 over E2, 0 minus E1, 0. This is the square of a number. That number is the one that I get by sandwiching this perturbation between these now transition matrix elements. So that second state is 0, 1, 0, B, B, 0. The first state is 1, 0. Obviously, this matrix element gives me B, and then I square it. B is real, so you don't even need the absolute values. So what I find is that GE1 at second order is minus B squared over E2 minus E1. Is this positive or negative? This number is negative. It's negative because the numerator is squared. The denominator, we've already put it in a form where this difference is positive. Does that agree with what it should? Should the correction to the first energy here, E1, be positive or negative? It should be negative. As it is, E1 is the ground state. The assumption is that there's 2 eigenvalues. This is the low energy. This is the high energy. This is the ground state, this is the excited state. We showed that the second order correction to the ground state is always negative. That because of exactly this reason, the numerator is always a positive number. The denominator for the ground state is always negative. So this acts like a downward pressure coming from the excited states above. I think it's called level repulsion sometimes. You can think of it as this energy is pushed down by all the ones above it. The energy above is pushed up by all the ones below it. So this energy is negative. We anticipate that the correction to E2 will be positive. GE2 at second order is that same kind of matrix element. There's only one other state that you can go to. Now this is divided by E2 minus E1, the state you have minus the state you want. Again, the numerator is b squared, and the denominator is the same thing, E20 minus E10. This is a positive number. This agrees with our expectation. Likewise, we can calculate the first order correction to the states. The state n at first order correction with a factor of g in front just to keep count, we said was the sum prime over all states m different from n. The state m0 times the amplitude n0, gh1 n0 divided by the energy you have minus the energy you want. So when I look at the correction to the state 1, the sum contains only one term. The only other state there is in the problem is the state 2. 2 gh1 1 divided by the state that the energy that I have is E1, the energy that I want is E2. This numerator is B. This denominator is negative. So I think it's instructive to write what this eigenvector is explicitly. So that at this order, the complete eigenvector 1 is the bare eigenvector plus the first order correction plus order g squared. This one was the column vector 1, 0. This correction is minus b over E2 minus E1 times 0, 1. So the approximate eigenvector that we have constructed is 1 negative b over E2 minus E1 plus order b squared. B is that number that quantifies the strength of the perturbation. So this is the approximate eigenvector corresponding to that corrected eigenvalue. So for this one, the corrected eigenvalue E1 is E10 plus GE11 plus order g squared. This is E10 minus b squared over E20 minus E10 plus order b squared. So you can test for free that this approximate eigenvalue with that eigenvector with that accuracy works as an eigenvector with that approximate eigenvalue to that same accuracy. Try multiplying them out and verify that it works. Likewise, we simply get the correction to the second state. Again, the numerator is b. This time the denominator is a positive number. So my full eigenvector to this accuracy was 0, 1 plus this correction. So I've got the approximate eigenvector b over E2 minus E1 1. Plus order b squared. And again, you can test that this works with this matrix to this level of accuracy. We are out of time, but it is possible to take that matrix and diagonalize it exactly. The full Hamiltonian in this setup was E1, E2, B, B. This is not hard to diagonalize and find what the complete eigenvalues are. You can find those eigenvalues and then you can take a Taylor series in those eigenvalues in B. And you can compare that when you expand in B, that the order B squared correction agrees with what we found explicitly coming from first and second order perturbation theory. So this is one of the simplest possible examples that we can work out. You have another comparably simple example on the homework. On Monday, we will continue with another simple example of a linear force modifying the harmonic oscillator. That's another one of these rare problems that you can solve exactly. And then we will talk about the limitations of perturbation theory. That's going to lead us to genuinely non-perturbative corrections that cannot be represented with a Taylor series. And that will lead us to degenerate perturbation theory. Okay, that's it from me. Any questions?
Thank you.
Thanks very much.
Thank you, Professor.
Thank you, guys.